We're going to finish up our time in physics in this academic year, talking about something that I consider to be one of the more interesting aspects of physics and represents the new age of physics that began probably in about the 1920s to 30s with Albert Einstein's discussion of the special relativity. So today and this week we're going to discuss special relativity. And this is distinguished from general relativity, which we will not discuss. Now, special relativity explains, among other things, why traveling to other star systems would be unreasonable because of our current level of technology. And once I explain some of these principles, I think you'll come to understand why it becomes very difficult to do these kinds of explorations into the far reaches of the galaxy. Now, special relativity in many ways resembles some of the more basic mathematical disciplines like trig, where their reliability is foundationally based on postulates, that is, fundamental precepts that are accepted, and they flow, everything else flows from those fundamental precepts in a logical way. However, one of the single most important thing that changed the world in terms of how we look at the world and particularly in physics was something called the Michelson-Morley experiment. This was an experiment done by two researchers, and they were essentially asking the question about the effect of the motion of the Earth on the speed of light. And they had a way of measuring the speed of light, and you can look the experiment up. It's quite famous, by the way. It also proved that light did not travel in a medium known as ether, but it traveled by other means, that electromagnetic radiation was distinguished from other types of waves in the fact that it didn't require a medium to travel in. But that being said, when they measured the speed of light, the idea was that if you measured the speed of light in the direction in which the Earth was traveling, Newtonian physics stated that the speed of light would be augmented by the speed of the Earth. Whereas if you measured it in the direction that the Earth was not traveling, in other words, the direction opposite the direction of the Earth, it would be inhibited by that much. And what was interesting was that they showed, quite unexpectedly, that the speed of light in a vacuum is entirely independent of the motion of the Earth. In other words, it didn't matter what direction you measured the speed of light, it was the same regardless. And this was quite remarkable because it foundationally smashed the idea of many of the Newtonian ideas in regards to the relative effect of motion, the additive effect of vectors, etc. Now, as it turns out, and you don't have to throw away your Newtonian physics, because in normal life, Newtonian physics is an absolute accurate estimation of how things really are. But indeed, it turned out that the Newtonian physics was an estimation as opposed to an exact measurement of how things really are. And that the estimations begin to break down when you talk about traveling at speeds that approach the speed of light. Now, most people think that Albert Einstein was one of the greatest minds that ever lived, and certainly the greatest mind that lived in the last 100 years. He did that primarily based on his enormous ability to perform what are known as thought experiments. He could think about things in a very logical manner and not let his presuppositions in terms of how the Earth seemed to be damage or influence what he thought, how his thoughts would go. And in the process, he developed two significant postulates which form the basis for the the theory of special relativity. The first of these things that he did was to define what is known as an inertial frame of reference. The inertial frame of reference, he didn't actually define it, he just restated it because before he came along, people talked about frames of reference in order to do the work that they were doing. But if you remember, the definition of inertia and an inertial frame of reference is the fact that a body at rest remains at rest unless acted on by a force, and a body in motion will remain in motion without acceleration unless an outside force influences that body. Now, Albert Einstein took this a little bit farther and stated that the laws of physics are the same and can be stated in their simplest form in all frames of reference, inertial frames. And that last part, in all inertial frames, is the critical aspect of the statement, because we make assumptions regarding the frame that we are personally in, and don't realize that those things that we are saying are also true in frames of reference that we are not a part of. His second postulate stated that the speed of light is constant in a vacuum and independent of the relative motion of both the source and the observer. Now this is basically restating what was shown in the Michelson-Morley experiment, but reaffirming it as being true. And once he started with those two postulates, everything else that we will talk about mathematically is derived from these first two postulates. So let's first talk about the effect of these postulates on time and spontaneity. When we talk about time and spontaneity, it seems as though the elapsed time for any particular race is the same for all the people who are observing that race. However, the relativistic speed's elapsed time also depends on the relative motion of the observer and the events that are being observed. And the important aspect of this is everybody in the picture here is in the same frame of reference, but let's suppose there was somebody on the moon that was watching. Their view and the speed, the times, etc. would be dramatically impacted by the motion of the Earth relative to the motion of the moon, and so forth. And so, that is what is sort of brought out by the statement that's being made here, is the fact that for the observers here, because they're all in the same frame of reference, the elapsed time seems the same. However, when you take people out of those frames of reference, then things begin to change rather dramatically. For example, and this is an example that is commonly used to try to show what we're talking about. If you have observer A that's sitting on the car, and this car is moving, and observer B, if those lights go off at the same time for observer B, because he is stationary, at the time the lights flash, it seems as though they are simultaneous. However, he notes that for observer A, the flash moves to the right side first because the thing on the right has less distance to travel than the light on the left. You notice if you go from the top picture, that's observer B's perspective. If you go from the bottom picture, you notice the light rays, because of the motion, the light rays are closer on the right than they are on the left. And so for him, it seems simultaneous, but not to observer A. The point being is that simultaneous events are not simultaneous for all observers. And if one observer is not in the same frame of reference as another observer, then the idea of simultaneity is not the same. And so the point being is that simultaneity is not absolute. And what we're talking about here is the phenomenon of time dilation. The phenomenon of time dilation is the passage of time being slower for the observer who is moving relative to another observer. So if you have one observer that is stationary and another observer that is moving, the time passes slower for that person that is moving as opposed to the person that is stationary. And that phenomenon, the fact that it is slower, is called time dilation. Now, obviously, if we're talking about speeds that are fairly normal, it's quote unquote normal, then we're talking about 10 to the minus eighth seconds difference. Nothing that anybody would be able to detect. But when you talk about speeds where close to the speed of light, this time dilation can become quite important. Now, let's look in the first, in A, you have an astronaut measuring the time it takes for light to go across the ship from a light source and then come back to a receiver. And the distance that light has to travel would be designated D. And then obviously if it goes to the mirror and back, that's 2D. And the time it takes to cross the ship and come back is called T sub 0. So the time travel is delta T sub 0 and the distance traveled is 2D. On the other hand, if you have a stationary observer that's watching the same event from the Earth, instead of D, which is what the astronaut's observing distance is, he observes a distance, the person on the Earth observes a distance of S times 2, because as the ship is also moving from left to right, in addition to the light moving up and down, it also has to moves left to right. And you notice that the distance S, 2S, is quite a bit longer than the distance 2D. And takes a longer time, because it's a longer distance, the speed of light being the same, it takes a longer time, delta T. Delta T0 was the one time, delta T is a separate time, which is longer than delta T. Now, if you look at the triangles, you note the difference, D versus S, and that the length is the velocity times delta T over 2. So that the hypotenuse is measured by the distance traveled by the ship and the time period it took for the light to travel to the mirror and back. So proper time is defined as delta T0, and it's the time measured by the observer that's at rest relative to the event. And in this case, it would be the astronaut. He is at rest relative to the event of the light passing to the mirror and back. The person on the Earth is not at rest. The ship is moving across and so for him, it's a different time. So delta T0 is the observer at rest relative to the event, the important point being relative to the event. And that delta T0 measures 2D. It takes 2D divided by the speed of light, which is designated as C. So delta T, which is the time observed by the Earth observer, is going to be equal to some correction factor gamma times the proper time delta T0. And mathematically, gamma can be calculated as 1 over 1 minus the square root of 1 minus v squared over c squared. Now you notice if v squared is not a fairly large number, then c squared will absolutely obliterate it, and it becomes 1 over 1. So at normal speeds that are normally achieved, this ratio of v squared over c squared is diminishingly small. and so you have 1 over 1. So gamma ends up being 1, and delta t is essentially equal to delta t 0, which is why in normal life there's really no correction that needs to be made for the time dilation that occurs. It's so small, the time dilation is so small that it doesn't really make a difference. But in situations where the velocity is quite large, then then v squared over c squared, it becomes a real number, and 1 over that number becomes meaningful, and delta t becomes meaningfully different than delta t 0.